Good afternoon, everyone. How are you? Hopefully you can hear me all right. Welcome to week 8 of COMP1531. That's what we're doing, isn't it? So Jake's away today. I'm sure you all know because he's probably mentioned it. My name is Hayden. I work with Jake behind the scenes. I think a small handful of you might have heard of me or seen me around somewhere. Occasionally I go and help out on the forum, but all in all I'm just here to help. So this week you're going to be putting up with me, and in particular we're going to be talking about a few key topics, which are not what's up on the screen. That's the wrong screen. This screen. A few key topics here. So week 8, we're not sure what we're going to be talking about tomorrow in the lecture. In the lecture tomorrow, we will either be talking about some kind of bonus activity. I believe that Jake's already sent out a bit of a poll that we'll be referring to. Though today what we're talking about is pretty defined, which is system modeling in the area of design, software design, as well as an introduction to deployment, which is a fun little topic that in particular has relevance within your third iteration. So hopefully we have a little bit of fun today. Let's get stuck into it. I won't kind of waste your time with extensive introductions, but because I'm sure you're all a bit busy, which might actually lead me to the one question I do want to ask before we get any further, which is how's everyone's iteration 3 going? Because I believe that's where you're up to at the moment. So I'd love to just hear how are people finding it? Are you managing it well? If you're struggling, don't blame Jake, because he didn't write the project. So if you're in pain, it's not his fault. It's other people's fault, unnamed people. But I'm sure you're having a bit of fun, or at least hopefully by this point in the course, you're starting to get a feel for it, because the kind of idea with the project is that, iteration 1 is somewhat new. It's not too hard. It's a little bit confusing. Iteration 2 is quite heavy. It's really what you would call like the hurdle or the hump, right? It's where you just have to figure it out. Like it's the first time you're genuinely tested to have to make sense of it, right? And iteration 3, hopefully you kind of get it by now and you actually just need to do the work. So I'm sure Jake said this before, but 1531, the one benefit, well, there's many good things about the course, but one of the benefits of the course is that it's not a rear heavy course. And a lot of courses at uni are rear heavy. They kind of start really slow, and then by week 7 you get an assignment, and then like bam, you just get destroyed at the end of the term and they have a big exam. So if you do feel a bit tired, that's okay, because it should have been more tiring, which just makes your work later a little less tiring. So let's get stuck into 8.1 though. So today we're going to be talking about design modeling. Now, let me just move my head back up here, and hopefully we can get some comments up if this works. Yay! All right, so we'll post some comments there if people say some interesting stuff throughout the lecture. So within the topic of software engineering, specifically within the area of design, we want to talk about system modeling. Now, system modeling, what does system mean? What does modeling mean? You probably have a vague idea of what those two pretty broad terms mean. We're going to try and tie them together today. And in particular, the reason we want to tie them together is because when you go and build, enterprise scale, industrial scale software, you don't just kind of say, oh, I have a problem to solve, I would like to go and write code for it. That's what you do for something quite small, like what you're doing on 1531, this really small project, where you just say, oh, we need to solve this problem, I'm just going to go and hack away at it. But in reality, when you are faced with complex problems, you will actually try and translate this complex system in front of you into something that's very high level and understandable. Many of you kind of do this already when it comes to things like pseudocode or documentation. You're already familiar with this idea of trying to abstract something and to simplify it before you actually go and build it. And in particular today, we're going to be talking about conceptual models as a broad topic, and we'll be talking about state diagrams as well as an example of how to conceptually model something, particularly something that is state-based in nature. So what is a model? What are the things that we might be dealing with in the world of modeling? What comes to your head? Now, many of you are probably STEM students who've done some kind of modeling in high school or heard the word model in particular. I feel like the one at the bottom here might stand out to some of you. Know the model of an atom, the atomic model. You've probably heard this a little bit in science more than anything else. For those who are thinking a bit more concretely, you have physical models, which are essentially model plane is a common term you'll hear people use. It's a small plane that is there to represent a much bigger plane. Just like this atomic model is here to represent something far, at a far different scale, in this case much smaller, and at a far higher degree of complexity out in the real world. I don't know about any of you, but I went through one of those educational experiences where I was given an atomic model throughout high school, and then right at the end of high school, my teacher turned around and said, actually, atoms don't work like this, electrons don't work like this. This was just a simplified model. And I was like, oh, that sucks. I thought I understood it, but the benefit, though, of models is that without them, we would just not be able to understand very complex systems. And this is what gets us to the specific topic of conceptual modeling. So if we look back at the previous examples we had here, the person in the middle and the boats on the right are examples of what you would call models, but they're not examples of what you might call conceptual models, because conceptual models are a bit of a more abstract way to understand complex systems. So all models attempt to represent a more complex system, typically. And complex is a very vague word. Sometimes it can be the same system at a different scale, etc. But a conceptual model captures it generally in a diagrammatic or visual way, in the sense that it's not a to-scale replica of something, but it's actually you trying to take something and essentially write it down. Put it on a computer screen, put it in a diagram, put it in some notes, turn it into a picture, turn it into a chart. All these different kinds of things. And this kind of idea of conceptual modeling can be true across a whole range of stuff. If you sit down and say, I want to figure out how much I'm going to buy a house, and I'm going to have to pay off a debt when I buy that house. If you were to sit down with a little Excel spreadsheet and look at your loan repayments and other things, that's a form of you trying to conceptually model something. You are trying to take something that's very complex, which is your income and your spending and loan repayments and interest rates, and you're trying to reduce it down to something simple and digestible. Typically, when it comes to conceptual models in software, which is what we're talking about today, the most common types of conceptual models we see are data models. They're essentially typically diagrams that help us understand how a system is made up of smaller components. So, if you think about your project, you'll be like, well, okay, I have a user over here, and I have channels over here, and some messages, and messages kind of exist in channels. There's like lots of messages in one channel. That was a terrible diagram. Lots of messages in one channel, and then I have users, but there can be lots of users in lots of channels. We have mathematical models, which we don't really chat too much about, but you kind of understand mathematical models. They're just formulas, right? Formulas are just there to represent bigger things, but more interesting ones are domain models, data flow models, and state transition models. Now, data flow models are just a vague term to describe the idea of how data flows through a program. Now, last week you would have done use case diagrams with Jake, so you're actually kind of familiar with this stuff. A lot of diagrams in software are really just flow diagrams in some way. They're a way of saying we start here and we go over there. So the use case diagrams last week are a form of conceptual modeling, quite literally. So you actually already touched on these topics. Domain models are typically about how components of software fit together. It's not actually something that we do much with languages like Python. It's something we tend to do more in languages that are do object-oriented design. So in particular, that would include things like Java, class-based aspects of Python, but you'll actually do a lot of domain modeling inside of COMP1511, which you do after this course. And then one of the most interesting types of model is a state transition model, which is how to actually capture something that has a series of different states. And this can be generalized to many, many things in the world. For instance, one example of a state transition model is how to model a traffic light or a traffic intersection, right? Most of you have driven or been in a car that has been driven, and you've gone to a traffic light, and you know there are different cycles in that traffic light, right? Maybe, you know, these cars turn right, then these cars go straight, then the opposite cars go straight, etc. There are a series of different states. So that's a big part of what we're going to be talking about today, because a lot of the other types of modeling here, you just kind of aren't ready to do yet because you haven't learned enough fundamentals. So data modeling you'll go and do, for instance, in some other courses, such as COMP1531. Domain modeling you'll do in a course like 2511. There's probably a bunch of courses where you'll do some mathematical modeling in. But today's about state transition models. That's the example we're going to get to when we get through some of this theory. So to this broader question like we had at the start of like, why do we have these models and like what are they used for? Well, predominantly models are used to predict the future, to understand the present, or to determine the past, or to look back at the past. But largely, if it's not about understanding something, it's often about predicting something. So sometimes when you have, say, for instance, a state diagram, or some other kind of diagram or visual thing, whether it's the atomic model, it is not just about how does it work, it's about let's make sense of the future. And you've seen this when it comes to things like climate change and global warming, right? Where what happens is you try and build a model of the world, you know, the temperature and the oceans and carbon and all of this, and they use that to predict sea level rise and temperature rise. These are all forms of models as well. But if you wanted the simplest summary, if we asked you at point blank, what is a model and how are they used? The answer would probably be it's really just to convey the fundamental principles and basic functionality of systems. It is not to articulate every ounce of complexity of a system. It is just there for the fundamentals and basic elements of a system. This is a bit more of an academic or formal quote from Kung and Solberg. 4 fundamentals objectives of communicating with a conceptual model are enhance understanding, facilitate efficient conveyance of system details. So there's like understanding, which is very high level, right? Like if you make, again, a model of global climate and temperature, you can help someone understand that, you know, the world's getting hotter. The second one, facilitate efficient conveyance of system details. Well, there are actually more granular details in the system. Again, like how much carbon's in the atmosphere, UV, whatever the hell's going on. There are these kind of system details. Provide a point of reference for system designers to extract system specifications. So this one, I can't really use the global warming example as much, but one really beneficial thing about a model is that it helps engineers understand what is going on. Because typically when someone comes to you, for instance, and they say, oh, I want you to build some kind of software. It's it's an app called UNSW Seams, and it's going to do all this and lots of text, and you've read the spec before, but you, as an engineer, sometimes won't be able to immediately translate that into some kind of system specification. Maybe you just aren't comfortable with it, or you find that hard to interpret. So conceptual models can be a good middle ground. So for instance, if someone comes along and says, well, here's the users and the channels and the messages, and I've put it in a diagram for you, you know, you've taken it from that raw text to diagram form, it makes it easier for an engineer or software developer to take it from diagram form into actual technical engineering specifications. So that's what that third point is. And then number 4 is documentation. We talk about the importance of commenting code and documenting your work. Well, the exact same thing is true just for general like record keeping. So when you do this documentation, when you write these draw or create these visualizations or diagrams, it's actually less commenting you might even need to do in your code, because you have other forms of communicating. Because remember, the point of commenting your code and the point of pseudocode and the point of all these things is just to help someone understand it. So this is more of that. Now, this is a more detailed list. This one I didn't write. This one I wrote here, so this is like a simpler one. It's not that these are true or false. This is just like a really simple explanation, and this one's a bit more of a detailed and thorough explanation. I talked before about different types of conceptual models, like data diagrams and data flows and domain models and stuff. There are two fairly fundamental types of conceptual models that can be broken up into two categories. One is a structural conceptual model. The other one is a behavioral conceptual model. Structural conceptual models tend to describe the system as it exists. It's like a snapshot of all the pieces of a puzzle. A structural conceptual model you could also understand as like a diagram of your house. You know, if you've seen, like house plans, if you've ever been on a website where you look up like a particular house plan, this would be an example of a structural conceptual model, because it emphasizes the static structure of a system. That is, this is just how it is all the time. Where simply these are the building blocks or the Lego pieces and how they, fit together statically. This is probably a model you're very familiar with, such as, again, the atomic model or something similar. Then we have behavioral models, which I think the easiest way, like we say, emphasizes the dynamic behavior of something, but in the simplest sense, behavior is a function of what you do over time. Like you can't have behavior that easily just by taking a snapshot. So how does software change over time? Which is why two examples of behavioral conceptual models are state diagrams, which we'll get into in a sec, which are just how you represent state of a system, and use case diagrams, which you did with Jake last week, which show how people, how someone might move through software. And these are all about flows. These are all about how does someone, change over time, right? How does something change over time? So let's actually go and explore state diagrams in more detail, because I think this, for those of you who are struggling to, ironically, for those of you who are finding conceptual models too conceptual, because we haven't actually gone and drawn anything, this should make it a bit more clear. So let's draw some state diagrams. And generally, we draw state diagrams of what we call state machines. So if something is a state machine, then we can draw a state diagram for it. And most things are state machines. You're a state machine, right? You wake up, you're in the bed, you're in the bathroom, you're in the car on the train, you're in a seat. You are moving between states all day. Most things in your life can be modeled as state machines, particularly anything that has behavior. So a state machine is essentially a system that consists of a finite number of states. That's pretty obvious. The state machine can be transitioned from one state to another through an action. So for example, a really, really simple state machine we can draw here is one of a door. So there's a door over here in the room, and that door could be modeled as a state machine, because it can either be open or it can be closed. And to move the door from open to closed, I have to close it. Thank you for being patient with my brain. And to move it from closed to open, I have to open it. That's it. So it's a couple of states and then some transitions between those states, describing how we go from one to the other. I saw a cockroach there's a cockroach on the wall. I don't have time to deal with it, so I'm just moving some stuff off the ground. So that's a really simple example of a state diagram. As you can see, emphasis on diagram. It's a diagrammatic representation of state. There is no strict notation for it. As in, there is not like, it has to be circles and it has to be lines with arrows or anything like this. They can be squares. You can change it around. And this is one of the exciting things, I guess, about modeling in general, is while there are conventions, it's a lot like style for code. There's some general conventions, but as long as it's consistent, you're okay a lot of the time, you know? It just kind of like consistency and clarity is the main thing. Whether you structure it differently or use straight arrows or curvy arrows, it's all kind of the same. But typically you'll have states in some kind of box, circles or squares, and transitions are some kind of line between things. That's the simplest crux of it. Other examples of state machines that we could draw state diagrams for are user interfaces within a given application, right? So YouTube could be modeled as a state machine. You're on the home page, you're on the subscriptions page, you're on the shorts page, now you're on a video page, and you know, to get between all those pages, you click on various links. So it's kind of like the links are essentially the transitions between different states of the application, and the pages you're on are the states themselves. You can model a network protocol as a state machine. This one might be a bit heady because of where you're at in your degree again, but you know, a network protocol goes through a series of you know, handshakes and messages and message received. Maybe a more concrete examples like a parcel. You ever gotten something delivered? You ever gone to the tracking website on DHL or FedEx or something, or Australia Post, where it says, you know, it was picked up in Shanghai and, you know, arrived in Kingsgrove and so forth? That's a state machine. You could model that by drawing a diagram if you wanted to. And then conversational interfaces, I mean, Facebook Messenger, Snapchat, whatever the youth of today use to communicate. I can't keep up. TikTok, I hear, is very popular. So, yeah, honestly, anything. Like, you could look around your room right now, wherever you are, and I'm sure you could find 100 things that you could model as a state machine that could have state diagrams drawn about it. Here is a more complicated example of a state machine, which is a parking meter. So I hope some of you again have paid for parking before, maybe with some coins, or if you haven't, you've seen your parents do it. I haven't really. I maybe have done this once in my life. I don't like parking or driving that much, I guess, because it's Sydney. But you think about your experience at a machine that pays for parking. If you're not sure on what I'm talking about, have a look at a parking meter here. That's a parking meter. This one takes in a card. We're talking about one that takes in some coins. This one looks really old. There you go. Anyway, there'll be one that looks like kind of modern that has coins. This one looks like it takes coins, right? Little screen, little coins. So you got something like this. When you get there, you're at like the initial state, which is the enter your parking bay. It's like, where'd you park? Tell us where you park. Typically, your car park might have a number on it. So you enter the car park number. Okay, that's one state transition. So I'm at the enter parking bay screen. I then input a number and I get taken to the next screen, which is enter duration. So now it says, how long do you want to park there for? 1 hour, 2 hour, 3 hour. And from here, I have two transitions that I can partake in. The first one is I can either cancel it and go back to the very start, or I can input a number of the duration, which takes me to the insert coin step. So when it says, all right, I know what park you're in. I know how long you want to be there for. Now give me the coins to actually do it. So what I do then is I enter some coins. And every time I enter the coin, I probably come back to this state as well, because I might have to enter multiple coins. So if I've entered coins and it's not sufficient, I have to keep inserting more coins. Or again, if I cancel it, the coins are ejected and then I go back to the start. And if there's eventually enough coins, I get to the confirm screen where it's all confirmed, and I can either click OK, which takes me back to the start, or I can click cancel, which takes me back to the start too, but would eject the coins. Now, that's state. This is a nice little example of a state diagram. It's not too complicated, but it's also simple enough for you to get. It's not too complicated. It's simple enough for you to get it, but it's complex enough for you to see how you might do something a bit more interesting than looking at the state of a door, which is kind of boring. When I mentioned before that there is no kind of universal structure for these state diagrams, the point there is that if you're ever drawing these, which you are and will as part of iteration 3, you shouldn't be stressed about getting it right or wrong. Because, for example, coin insert here should probably be a bit better clarified. And for example, see how we've got these coins ejected thing? Notice how both cancels eject coins. There's probably a state here that we're not representing, which is between, a screen like insert coins, and ejecting the coins and then finishing. So it would actually probably be very reasonable to create a new state here that's like ejecting coins. So that say, maybe I can, just gonna take a screenshot. So for instance, like here, I might actually say, what's actually kind of makes more sense is if I was to have a new state here that was called ejecting coins. And then what actually happens is that when insert coins is cancelled, it comes here. And when confirm is cancelled, it comes here. And then when ejecting coins is finished, it comes here. You know what I mean? Like, you can kind of imagine that ejecting coins could be its own state. And that actually kind of makes sense, because what you want to do in a state diagram is you want to actually describe like moments in time that are kind of more than a split second. And then it's like, well, could I take this further? When I do enter duration and I input the number, should I have an interim state that's like processing input? And then it's like processing complete? It's very open-ended. There is no hard science to it. It's a very human experience, because fundamentally you're drawing this to convey enough information for someone to understand the nuance and behavior of a system, but not so much that they don't actually get what's going on. Right? This is much clearer than giving someone a electronics diagram of how the computer inside the parking meter works. But my point that I'm trying to get back to is that this could be slightly more nuanced. It could be slightly less nuanced. So don't stress about it being absolutely perfect. Here's something that was missing from the diagram before. A timeout. You ever gone to a parking meter or any kind of ticket machine ever? Opal machine in Sydney? You go and start doing something. Or McDonald's. Who's been to McDonald's? I've been to McDonald's. God knows. You go order. You type in large fries, and then if you don't do anything, it'll eventually a minute later say, "Hello, are you there? Hello." And if you then don't do anything, it'll just cancel your order like another minute later. I don't know what the timings are, but that wasn't really represented by this state machine here, particularly that like automatic canceling. How do we represent that? Well, you could maybe do what we did before, where you have another state for, like, how do you represent 5 minutes elapsed? Is 5 minutes elapsed a state, or is it a transition? That's an interesting question, isn't it? Because if it's a transition, that doesn't quite make sense, because I guess it does. 5 minutes elapsed. Yeah, it's probably a transition. So you're at the insert coin screen, and then you either insert a coin and it's not enough, you insert a coin and it is enough, you cancel, or 5 minutes elapses. And if 5 minutes has elapsed, then you go back to the start. Or you go to the coin eject state that we drew before. Should cancel and 5 minutes elapse be different lines? Or should they be the same line? That's up to you, right? That's another example. There's no hard science to it. You could have them as separate lines, you could have them as the same line, whichever you feel makes more sense. And then one thing we'll try and do quickly is to really tease this idea out. Can we model the Opal card system in Sydney? If you haven't been to Sydney, if you're one of those international students who've been stuck overseas with COVID and haven't had a chance to come to Australia, firstly, I'm very sorry. That really sucks. I know a lot of people in that boat. But secondly, think about any transport system out there you have in the world, because most transport systems are like this, right? Sydney's just got a particular one. So how would we model? I might even do this one in a diagram tool, because I'm feeling sick of MS Paint today. You can, oh, by the way, where do you draw diagrams like this? Well, I wouldn't recommend drawing it in a simple paint tool, but probably one of the best ones is I think that's free is just app.diagrams.net. There's a whole bunch of these around the internet. I'm sure there's ones with free trials or that are free that I don't know about. Microsoft obviously has their Visio and mirrors what I use at work, and Figma is an online tool now that has a tool called FigJam where you can draw stuff. So there's tons and tons of stuff. Draw.im. Yeah, draw.io, which I think is what you're referring to there, Paul. Maybe I'm wrong. Unless there's one called Draw.im. That I think got renamed to app.diagrams.net for some reason. But this is a nice little tool. Actually, we can just do it here. So let's say we want to draw an opal card system here. Well, like, what are the states associated with an opal card? Well, like, what state's your opal card in? Are you trying to model the state of the system or you or the opal card? Let's do the opal card. So let's think about it. And I know all of opal's rules, but let's not complicate it too much. You kind of have like not tapped on, right? You aren't tapped on anywhere. Okay. And then you go and you tap on. You tap on at a station or a bus or something. Think of a train station. Okay, so you tap on. All right, and we can tap on. Or specifically, tap on is like a verb. I should actually have that here. This should be tap on. Because like these are states. Tap on is not a state. Tap on is an action. So this should be tapped on. So think about language, and language matters here a lot. So I'm not tapped on, and then I tap on, and now I'm tapped on. And then you say, all right, well, what happens next? Well, when you tap off with your opal card, I'm not sure if many of you know this, you go into essentially a 60-minute window, where in that window you can kind of transfer to another mode of transport. And in fact, it's actually even more complicated than that, because if you tap on at a station, for instance, I don't know how to make this line curvy. Oops. If you tap on at a station and you tap off within 15 minutes, it actually gets reversed, your charge. So you actually don't get charged. So if you tap on and you're tapped on, but then you tap off at the same station, within 15 minutes, you don't get charged. But now let's say you tap off. So now if you say you catch a train from, Strathfield to Central in Sydney, you then tapped off mid-journey, you would say, because the way that things work in Sydney is that if you tap off at a train, if you tap off somewhere and then you tap on somewhere else within an hour, it just kind of like extends that for you. So for instance, if you tap off, you come from Strathfield to Central in Sydney, and I know I'm relying on some people that are familiar with Sydney, but I'm going to assume most of you are. You go from Strathfield to Central, you tap off, and then let's say within 60 minutes, you tap on to another station like Town Hall. That's considered part of a bigger journey. So now I've got like tap off here, and now you'd say, well, if I tap back on somewhere after if I tap back on same mode of transport within 60 minutes, I'm tapped back on, right? And the thing is, like, I haven't thought about this too much, but as you develop this, you shouldn't be afraid to start, because there are clearly some problems with this, some things that won't make much sense. Because if you tap off mid-journey, but then you tap on within 60 minutes on another mode of transport, it kind of starts you on a new trip, a new kind of cost. And if you tap on after, like all these rules start layering on top of it that can make things really complicated. And, how do you deal with balances? Okay, so you try and tap on, but if you then if you try and tap on but you don't have sufficient balance, what in the world? Tap on with insufficient balance, it should just continue to have you not tapped on because you didn't actually get to tap on. And I have to go and rename this one so that this one is a bit clearer. I now have to call this one tap on with sufficient balance. You know, so it's this constant iterative process of just working through it and slowly expanding out your ideas and making sense of things. And that's really the process. Now, the last thing, actually, I should ask, is there any questions about this so far? I'm about to do one last example before we have a break, so I just want to check if anyone has any questions. Invalid card. Yeah, that's also true. We could make another state here where we go from, you know, tap on with invalid card for sure. There's lots and lots of examples. And this is actually one of the challenging things about this whole experience generally, is that you not only have to do this intelligently, but you have to ask yourself constantly, is this too much info? Am I missing info, or am I flooding you with information? Those two questions are really hard to answer because there is no perfect answer. And it only really comes from showing people. Nathan says, why can't tapped off and tapped off mid-journey be the same? That's a good question, because if you've never tapped on, the transitions that you can do from having never tapped on are different from the transitions you can do mid-journey. For instance, if you've tapped off mid-journey, you can tap back on. Well, and then it's a good. Okay, so here's the good question. What are you trying to achieve? That's something we haven't even talked about, which I've glossed over. What is the point of this diagram? You don't just draw a diagram like this, right? Are you here to explain to stakeholders like Sydney Transport or the government how this works? Are you trying to explain this to developers who are building the system? Are you trying to explain this to customers who are going to use the system? Are you trying to explain it from a time perspective or from a money perspective? All of these questions inform what you actually do here. So do the question Nathan has, which is, why can't tapped off and tapped off mid-journey be the same? Well, the answer is they probably can if your objective is just to show whether you have a valid ticket. In fact, if you just need to show if you have a valid ticket, there's kind of not much point to the state diagram. What I've kind of started to do here, the direction I've kind of headed in, is actually more to do with how much it costs. You know, to actually show like a state diagram and relate that to how much it might cost. Because, for instance, you know, if you tap off within 15 minutes, you aren't charged anything. Okay. But again, it's like, what's the aim? That's the short answer to the question. There is no like, why can't it be this or why can it be this? It just depends what you're trying to do, because this could get more complicated. If this was to be an engineering diagram, something that you're mainly trying to model something for engineers, you might include a whole lot more error cases. You know, a whole bunch more edge cases to help them understand how these things flow through. And Stephen says, how about negative balance? Well, is negative balance a state of a card? Yes, I guess it is. I guess we could have another one. It's like, well, you know, you have a negative balance here. But then it's like, how do you actually, what even is that? Because like, can you have a negative balance whilst you are tapped on? No, you can't, because you can't actually tap on. You can't actually hop on public transport if you have a negative balance. So it's kind of like, now we have like a tapped off negative balance state, and we have like or not tapped on positive balance state, and we have like a not tapped on negative balance state. So it's like, all right, well, how do I do this now? Okay, so I'm not tapped on, so, well, if I tap off at the same station, like if I reverse the charge, I can't be negative, right? Okay, well, if I tap off mid-journey, I could have a negative balance then, because if you have $2 and you go somewhere and it costs you $3, it might be negative here. How do I add that in? Oh, I don't know, you know, we'll figure that out later. But if you're not tapped on and you have a negative balance, you can obviously recharge. But then you think, oh, I'm not tapped on, but I don't have to. I can be tapped on and recharge too. In fact, I can have a positive balance and recharge anyway, can't I? You don't have to be negative to put money on it, and then you think, it's not making sense. So, I mean, I don't have an answer. There's no model answer for this. I go through this example, and I don't really have like this is the finish point, because the thing I'm trying to convey is just the complexity of it. The fact that you have to just sit down and think about it, and sometimes it takes a lot of time. Steven says, let's say you only have $5 and you try going to the airport by train. Well, yeah, how do you deal with nuanced cases, such as, like, and again, this is where it gets kind of complicated. And I'm obviously this is complicated because I've lived in Sydney for 10 years now, and I'm familiar with Sydney's transport. But it's like, if you, for instance, in Sydney, have $5 on your ticket, if you go and hop on a train, and that train trip could cost you $2 to $8, they will let you hop on that train, because you only go into negative if you cost more. But in theory, you might not need all that money. Whereas if you have $5 and you go and hop on a train that costs, or a ferry, for instance, that costs $6 to $12 or something, I don't know what it costs, that won't let you hop on. So now you have to account for those two different states. And suddenly, if I was drawing this, I'd get to this point and I'd start just being like, my head would hurt. I'd be like, I feel like I am not getting it. So what I would do is I would stop. I would go back, and I would go back to think about what Jake talked about last week with use case diagrams. Go and start writing things out. Like, write out different use cases. Start drawing it out somewhere else. Don't force yourself to come up with something perfect on day one, just because you want to. It's pretty reasonable to assume that some of these things will just take time for you to work through a few different ways. And I'll show you something from my work, that I want to show you, because I was trying to do some conceptual modeling the other day for some work stuff, like, so the private work I do, teaching at the uni is not my full-time job, and I'll show you. This is what I ended up with, right? This diagram here. This is a conceptual model. This is me trying to design a product landscape, right? And I'm trying to figure out how to convey it. It's very complicated. How do I convey this to people in a way that engineers can understand and other people can understand? And this is what I ended up with so far. And the reason I'm showing you this is because how this actually started was I actually started drawing something like this up here. I won't show you all the details, but I started drawing something like this up here, where I was like, yep, okay, and then I grouped it together, and then I started drawing something like this. So I took all these boxes and I started joining them together. This is me trying to model something. And then I didn't like that, so I tried to draw it a different way, and then I tried to draw it a different way, and then I tried to draw it another different way, and then I was like, this is too simple. I was like, I've oversimplified this. Sometimes your models can be so simple they don't actually convey what they need to. So then I stopped and I pulled it all apart, and I said, all right, well, let's make this complex again. Let's go and get all this different stuff. So I ripped it all into more detailed pieces, and then I said, well, let's try and understand the relationships, and I, drew all these different things, and again, that wasn't quite working for me, but I was getting there. You'll see that, like, compared to this one here, this one started to be grouped a bit better. And then I got down, I tried grouping it a different way to see if it makes sense, and then I ended up with something like this, where I was starting to group it better, and then I ended up with something like this, and something like this was also where it's kind of ended up. But it's like, after all of that, this is like maybe 45 minutes a night for a week kind of thing, right? I then was like, tried some other stuff, and I just ended up with this, and then I turned around the next day and I was like, I can take this even further and simplify it, and I ended up with that, which conveyed everything I wanted to. Now, I'm not trying to say this is very complex. There's an element here where if I was smarter, this would have been much less arduous. But what I'm trying to articulate to you is that this isn't a linear process, right? It's not like sitting down and baking a cake. And if you're not sure what the next step is, you stop. This is actually an experience of iterating through things and learning and trying stuff and showing this to people along the way. Like, I would show something to someone and they'd say, yeah, but I don't see where this is here. So just like we had Nathan say, Why can't tapped off be the same thing? Or how Stephen says, what about negative balances? These are normal questions that you get asked on the journey of trying to model something. Arjan says, why don't you show them all three of them? This is a good question. Sometimes we do have different models for different purposes. I didn't in this case. I had one thing I wanted to do. But yeah, in other cases, sometimes you will have simplified models, more complex models, etc. And the last thing here, the last part of today's lecture before we take a break, so we'll probably run for another 5 or 10 minutes and then we'll take a break, is an example of a conceptual model that was used in the 2015 solar car race from Darwin to Adelaide by a UNSW student. So one thing that, a problem that we were presented with back in 2015 was that we were competing in this solar challenge where what you do is you and a bunch of other university teams, you would come together, you would build these cars. You might have seen these around campus, or well, UNSW has one. Lots of unis have them. You would build these cars. These are the best teams in the world. A lot of them in Europe and the US, and you would drive them from Darwin to Adelaide. Right? You would drive them along 3,000 kilometers along the highway, and there was kind of a problem, which was, how do you you have a fixed battery size, right? So it's like you only have so much battery. Think of it like a fuel tank. Imagine if I said to you, you can drive a car from Darwin to Adelaide, but you can only fill up your car once. Okay. Well, how fast do you go? Or, like, let's imagine, like how fast do you go? It's a little bit like running or cycling or driving. If you go too fast, you'll burn more fuel and you'll tire yourself out, right? It's not very efficient to go really fast. If you go too slow, you'll lose. So how do you get there the quickest, right? Anyone who's done a marathon or something or running kind of knows this. If you run too fast, you'll tire yourself out and kind of collapse. If you go too slow, you'll lose. So where's the line between that? Well, to answer that question, someone actually tried to model this experience, right? Because if you think about it, to drive from, say, Darwin to Adelaide is a behavior. It's something where, at any given point in time, you're driving and there's certain conditions that are interacting with you. So what they did was they actually modeled this, they made a conceptual model of this race based on some previous research, which you can look at in the slide. This is a student who's probably about, well, I think I'm about 10 years older than you all now. So this student's probably like maybe 12, 13 years older than you. On average, some of you are older and younger. They did a big thesis where they looked at like the dynamics. This is from a previous event. Anyway, the point was the conceptual model was to represent the energy usage of a solar car as it drove from Darwin to Adelaide. So it was to try and make a state diagram or a state machine that would be able to tell you at any given moment how much energy is being used. And if you want me to relate it to the running example, it's like, imagine if I said to you, run from Sydney to Wollongong, or from Sydney to Newcastle, or from UNSW to the airport. This would be the equivalent of saying, I'm going to model something where every 10 meters, I'm going to be able to model how much energy, how tired I am, how much energy I need to exert, so that I can decide how fast to run. Because at some points, you might be able to run faster, right? Like running down a hill. But you want to go slower running up a hill because it's more tiring. So this state machine essentially looked at things like wind speed, wind direction, a few other things, and it said, all right, I'm going to break up the entire race, which was, imagine this is a 3,000 kilometer race. Let me just make this a bit bigger. We got a 3,000 kilometer race like this, and I'm going to go and break it up into a series of little chunks, kind of like samples. And these samples might be every 50 meters or something. Because it's very, like everything in computer land, you have to break it up. Now, I don't know why these samples are at different heights. I guess maybe imagine those heights are like speed. So imagine this is like, 0 kilometers on the trip, and this is 3,000. And then this is how fast you're going to go. Right, so this is like your speed like this. So, for each of these like 50 meter segments, you're going to go at a different speed. And that speed's going to be determined by how fast is the wind going, right? Because if the wind's coming really fast, in like, think of it like running or cycling, right? If the wind's hitting you really hard, you're going to go slower to burn the same energy. If the wind's coming from behind you, you're going to go faster. If there's more energy coming from the sun, you can go faster. If there's less energy, you can go slower. If there's more clouds, sometimes you might be able to go faster or slower, depending on what the gradient of the road is, depending on where you are orientated, depending on what the weight of the vehicle is. Like lots and lots and lots of factors come into this. Tons and tons of things. And what was interesting was that when you build a conceptual model of this, you have to decide what to ignore or not. Have you ever heard the phrase like ignore friction? Or like let's disregard friction when you're doing or let's disregard wind resistance. Who remembers that from high school? Doing like projectile motion. They'd be like, Charlie throws a ball across the room. Where does the ball land? Ignore air resistance. So you'd actually have to ignore certain things in this model and not ignore other things. For instance, the amount of power that the motors draw was a bit complicated to model, so we just didn't model it. But we knew it was there. We knew it was like 1% of the power loss or something like this, but we just didn't model it. There are other things too, like cloud cover is really difficult to model. Like how much sun are you getting is really, really hard, because things like the Bureau of Meteorology, they'll actually tell you what the solar output is on a given square meter at various points of the day. So you could go outside right now and they just measure from the sun, like, you get, 100% energy, 80% energy. If there's really, big clouds, maybe it's 2% energy. But they're obviously measuring that from one place, and where you are might be very different. Some teams, some really advanced teams, they had more complex models than we had, where they would actually do what we call cloud chasing, where they would actually have more real-time models that would look at the sky and actually try and go faster or slower to keep up with the clouds so that they had more time in the sun. But then that has to be balanced against the problem that if you're constantly speeding up and slowing down, you're going to get tired, right? And again, imagine yourself on a bicycle. If you're trying to stay in the shade to stay cool, there's a point where if you're pedaling really hard to catch up to the shade, it might actually tire you out more than the tiredness of experiencing the sun on you, So the point is, I'm just conveying the landscape. A conceptual model had to be built that took in all these different inputs as essentially a state machine that was built where it was like you're moving from like a 50-meter state to another 50-meter state, and each of these states had all of these inputs come into them, and you would calculate the speed. Now, there's no doubt that you could have just tried to code this problem. But the guy who wrote this, Tom, really, really genius engineer, if he didn't try and model this, if he didn't try and document it somehow, he probably would have come up with a worse outcome, because he wouldn't have been able to think about the system holistically. And if he didn't model it, I would have never been able to understand it when I did some work to help him out too. So, if you're ever presented with a challenging problem, to kind of summarize to get to the end of all of this, if you're ever presented with a challenging problem that you don't know how to solve, or you don't feel like you have a grasp on, and if you're not sure how to go about building it, or you're not sure how to go about conveying it, just start drawing stuff. Just start drawing your conceptual model of the situation and keep at it, and eventually you'll have something and you say, this makes sense to me. I get this. This is simple enough to be understood, but it is complex enough to actually capture the system. And then from there, you can show it to someone, or you can go and use it to build things. Or you never build things and you just use it to predict the future if you're outside of the world of computing. But typically in computing, we generate models to build stuff is the main reason we do it. Because software is really hard to understand, right? Like, you can show someone a car and they can look at the car and be like, all right, I get what this is. They can take it apart really easily. You can lift up this and they go, I can see what's there. But in areas of like electronics and software in particular, modeling is excessively important, because probably even, no one looks at code and electronics and goes, oh, I can see clearly what that's doing. Anyway, Any questions about that? Otherwise, we'll take a break and we'll get into the second part. I'll just give you all 20-30 seconds to wait for the YouTube lag to catch up. See if you have any questions. Was I part of the Sunswift project? Yeah, I was from 2014 to 2017 inclusively. That's why I'm talking about it, because that's the closest examples I have. But, you know, this is not. There's a million things you can do with this stuff, so it's not. You know, it's my favorite thing about this whole area of modeling is that I love things that communicate things clearer. I love things that help you understand it. I love things that help you plan. And I love things that you can apply to nearly anything. So, like, great topic, great fun topic. I hope you take away a sense of how, when you're dealing with complicated problems, you can now have a bit more confidence to go and say, I'm going to go and draw something, is the main point. And it doesn't need to be code. You could conceptually model your life or your future plans. Do it with anything. Anyway, let's take a break, and then we'll get stuck into deployment. So let's regroup at 12:15 in 5 minutes.